Here we have a cool mist humidifier. Maybe you can't see the vapor that's coming out or the mist that's coming out, but here you go. Okay, and obviously, right, this is not hot. Ouch. Nah, it's not hot. Okay, so because it's not hot, we know that the process that's going on over here inside this thing is definitely not boiling. Take a look. Okay, I don't know if you saw that, but anyway, that's not boiling. This is definitely evaporation. Okay, and this is the product of evaporation. That's exactly what we're going to look at in this video. Just a side note, for pure physics student, this will be part 1 of your thermal properties of matter, but for science physics student, this is, you just have this part for this chapter. Okay, so let's look at the content. Okay, we are going to cover this like 5 main points over here. Okay, I think I covered like half of it or quarter of it in class. Okay, so I think it's pretty straightforward. Okay, first thing, internal energy, right? Okay, so from here on, let's just follow the content page, and I'll put in the link in the description below, like at which point of time am I talking about what. Okay, so you can like skip forward if you are already familiar with the concept, but for those who are not, I think this is a good time for you to revise whatever I went through in class. Okay, yeah, and pardon my voice because I'm down with the flu. All right, first thing, internal energy, right? So when we talk about internal energy, we want to remember these two, potential and kinetic energy. I think all of y'all should be familiar by now what kinetic, when I mention potential energy, what do I actually want to know, and when I mention kinetic energy, what do I actually want to know. Okay, so first thing, when I mention kinetic energy, the easiest thing I want to know is I want to know how is the temperature changing with relation to kinetic energy, and with temperature change comes speed change. Okay, and we are going to talk about like how particles react when the kinetic energy goes up or down. Is it like moving faster? Is it like moving slower? Second thing we want to talk about is potential energy. Potential energy usually links with state change, but take note, apart from state change, it can also we can also talk about potential energy when an object is undergoing expansion or contraction, right? Because what we are actually looking out for in potential energy is actually the average distance between the particles. Okay, and we know that in expansion the distance increases, and in contraction the distance decreases. Okay, and more importantly, during state change this distance changes drastically, okay, or significantly. Okay, I mentioned the idea of average in class, so I'm not going to go through that. Yeah, okay, then we go to state changes. What is heat? Now heat is just a form of energy, thermal energy, and temperature, right? Temperature is not a measurement of heat. Okay, in fact I think a better defined, right, temperature is actually a measurement, sorry, let me write here. So temperature is actually a measurement of kinetic energy. Okay, and we'll talk about this later on, but take note that temperature is just a measurement of Ke, because when Ke doesn't increase, temperature doesn't increase as well. Okay, so this is the best way to talk about temperature. Now we have state changes here. I think you are quite familiar with the state change. Okay, just take note of the two new terms that we introduced here: exothermic and endothermic. Okay, endo meaning enter, exo meaning exit. Okay, and with exit you mean lose, with enter you mean gain. All right. Okay, if you need to take a look, this is what we have summarized at the end of that lesson when we talk about internal energy. Okay, and here is the conclusion that I want you all to know. Okay, if you're not able to derive this conclusion, please let me know. Okay, because this is like the heart of thermophysics. Okay, like for kinetic energy, if you don't understand what temperature is, yeah, you have to clarify with me. Okay, okay, now we talk about melting and freezing, right? So what's melting and what's freezing? I think everyone by now should know. All right, so melting is a process. Okay, a process when a substance. Okay, both of them talks about a process. Okay, so in fact I'm just going to write here a process when a substance. Okay, so melting is goes from solid to liquid, while this freezing is a process where it goes from liquid to solid. All right, and for uh sorry, okay, for pure water, melting occurs at 0 degrees Celsius for pure water, and it's the same for freezing as well. Okay, and I think we can very safely assume that for melting it actually gives off heat. Sorry, it actually takes in heat, while for freezing, right, it gives off heat. Okay, now, and just one thing to remind you all, in this process of taking in and giving off heat, right, taking in and giving off heat, temperature, the change in temperature is actually zero. Okay, in other words, right, during this process, right, energy is solely given to the potential energy of the particle. Okay, because remember that when potential energy increases, right, our state change. Okay, and because we know that state changing because of the average distance that is increasing. Okay, and temperature change is zero, meaning to say kinetic energy is zero. Okay, so if I supply you with 10 units of energy, okay, 10 units will go to potential energy, 0 units will go to ke. Okay, so yeah, pretty straightforward. Okay, because there's no change in temperature, all the energy must go to potential energy. Okay, and then we talk about the cooling curve, right? So for the cooling curve is here. Okay, I want you all to take note of why during state change the melting point will be constant. Okay, and this is the answer that we came up with. Okay, if you need, you please pause the video over here. Okay, I'll not like stop for you. Okay, so let me move on. We also talk about the heating curve, pretty much the same thing. Okay, so yeah, please craft your own answer. Okay, the question can be similar as to like explain why the temperature of PC remains constant. Over here you might want to ask, explain why the temperature of CD remains constant. Okay, and you also can ask, right, why is the time taken for AB so much shorter than the time taken for CD to happen. Okay, so T of AB is so much shorter than T of CD. Why? Right, because we mentioned this also, because over here you are just weakening the bond, over here you are trying to break the bonds. Now relate these to in terms of potential energy. All right, so in terms of PE, right, this is what's happening, right? Like I have particles here and they are weakened. Okay, so maybe the structure become like more flexible. Okay, but over here this is for C to D, right? I mean A to B, sorry. But you realize that for C to D the distance increases even more because you're trying to break the bonds. Okay, so this is for C to D. Okay, so like you measure the average distance between particles here. Okay, you realize that this, the last diagram, triumphs in terms of average distance. Okay, so let's just fill this blank. Same thing. What is boiling? What is condensation? It is a process. Okay, so I'm just going to write here a process when a substance, okay, goes from liquid to gas, right? And this one would be goes from gas to liquid. And for pure water, right, you have to memorize this. Okay, and I think it's pretty straightforward and pretty easy to memorize. For pure water, this will happen at 100 degrees Celsius, right? So happens at 100 degrees Celsius. Okay, and just to take note, same thing for boiling. It's a process where it takes in heat. For condensation, it's a process where it gives off heat. And same thing, we want to like recognize the fact that these two process, right, the change in temperature during these two processes will also be zero. And not only so, because it's zero, because the change in temperature is zero, we know that the change in Ke when these two processes happen, right, must be 0 joules as well. Okay, and because the change in Ke is 0 joules, we know that during these processes, right, any energy given is given to change its potential energy. All right. Okay, so just gonna write here as a quick remark. Change in potential energy equals to energy given during process. Okay, so if I give it 10 joules, if I give it 10 joules, then it will gain 10 joules of potential energy during this process, right? All the way until the process ends. Yeah, then maybe K will start to increase, P might start to increase also, yeah, depending on like whether the object expands or contracts. Okay, and yeah, finally we are done with like state changes. Okay, so basically this is a summary of like what we just went through for the past, I don't know how many minutes. Okay, but here we are for the next part, which is boiling and evaporation, which is what the video shown at the very start of the entire short lecture, right? And these are the differences between boiling and evaporation. Yeah, I want you all to take note of a few things. Nothing to copy here, just maybe you want to underline certain things that you know might actually be important for you to note, like the main differences between boiling and evaporation, right? So this is a both, right? Correct, both is a process where it changes the state of the water. Okay, and over here bubbles are formed. We want to ask ourselves why, right? And here there are no bubbles formed, so we also want to ask ourselves why, right? And it actually has to do with where it occurs. Okay, right. Okay, so let's go into the idea of boiling and evaporation. Okay, so draw box here. Explanation of evaporation using a kinetic model, but before we can really understand what's going on in evaporation, we might want to take a look at what's boiling first, right? Okay, so for boiling, I'll have a cup of water, a beaker of water, and then I'll have a heat source, right? Then after a while, of course, you need a tripod. Okay, now after a while, right, you'll start to see bubbles forming, and it's not just like in the central region, it's like throughout the entire liquid. Okay, and then eventually the bubble will like burst as it reaches the surface. So what's happening here, right? So basically the Ke. Okay, now a lot of people, when you ask, right, people like where does boiling take place, okay, maybe they'll tell you like at the surface, because like this is the area where the bubble pops. Okay, but what's actually happening is like actually taking throughout the entire liquid. These bubbles you see, right, are actually like pockets of gas, right? And like what exactly is this gas? Yeah, so it can't be like nitrogen, or it can't be like what, chlorine gas, right? So like it's definitely like water vapor. And the reason why water vapor become gas, because it has already boiled. Okay, so like it has started to boil over here and it's trying to escape. Okay, and that's why like the bubbles will float up. Okay, why is it trying to escape? So first thing first, boiling occurs throughout as water particle gains Ke, right? And enter the process of boiling. Okay, so like why does the air bubbles all like start to go up then? Why doesn't the bubble sink, right? And I think this is very clear cut, because the density of the bubble is lesser than the density of water. I think I use a different ink here, right? So the density of bubble is lesser than the density of water, and anything that is less dense will want to float up. Okay, and that's why like it rises up. Now then we talk about like evaporation, right? So like for evaporation, we have no heat source. We just put a beaker of water here, right? And then we ask ourselves, hey, how come like after one day we realize that maybe the beaker of water, the level decreases, right? And then we say like, oh, it's this process that we call evaporation. Okay, evaporation also produces mist, but the mist here, right, for boiling, right, this mist is hot. You know, the mist that's produced in evaporation, if you can even see mist in the first place, this shouldn't be hot at all, right? And that's why like I was able to touch the humidifier mist. Okay, so what the humidifier does, right, is that it hastens the process of evaporation. Okay, usually the process of evaporation is very slow. Okay, and because it's very slow, right, you usually won't see the mist. Okay, so no mist. I think if you have drawn it, you just put across here, right? There won't be any mist. Okay, so what's happening in evaporation? First, you have to know that inside the atmosphere, right, they are like water droplets. Okay, and then you have like other gas particles like nitrogen, like carbon dioxide, like maybe the gas that comes out from the human body, you know. Okay, so whatever lah, right? So you have all these gas here. Now what's happening here is that this liquid particle is actually ready to like join in the atmosphere. And what it does is when he realized that it has enough energy, right, to escape into here, okay, it will actually escape. Okay, and this actually causes evaporation to occur. Now and if therefore, you know, and if therefore your atmosphere is very very thick, okay, so your humidity is very thick, right, what's actually going to happen is that there won't be enough space for this particle over here to like penetrate into the humidity. Okay, and therefore like evaporation might occur at a much lower rate. Okay, so for evaporation to occur, right, so we are talking about average K here. So remember how we talked about average K at the very start over here. Okay, now if the average K is 10, okay, maybe this thing is moving at 1 meter per second. This thing might probably move at 11 meter per second. Okay, and when you add 11 and 1, oh sorry, if the average is 10, sorry, yeah, if the average is 10, you know that, okay, so if you add these two up, 1 plus x, and you find the average between these two, you want it to be 10, right? Okay, x has to be 19. Okay, solve for this and you'll get x equals to 19. So while there are particles that are very slow, there are also particles that are very fast, and usually the fast particles will reside on top, okay, of the surface, or because like they're making their way up to the top. Okay, and what's actually happening is when evaporation occurs, a particle with the highest Ke, particle with highest Ke escapes from surface. Okay, so as it escapes from the surface, right, the average Ke of liquid will drop. Okay, yes, and I think that's about it. And that's the reason like why you usually feel let's see, okay, so in fact you might want to ask a question, right, as to like why do we have a feeling cooling, why do we have a cooling sensation when our sweat evaporates from our arm, you know, like after we exercise or something. And this actually tells you the reason why, because the average K of your entire skin surface will actually drop when like the liquid evaporates, and when K drops, you know, temperature drops, right, you know, so that's why you feel cooling. All right, in fact evaporation actually takes heat away from your body. Okay, now our water evaporate faster in vacuum or under normal atmospheric pressure. Okay, we understand like this analogy, right? You should be able to answer this. Okay, answer be in vacuum because like there are like no particles in vacuum, and therefore it's very easy for the particles at the top of the surface to escape into here, right? Okay, now explain why a person experiencing fever usually feel cold when his body temperature is already hotter than usual. So we have to define, right, why would anyone feel cold? We feel cold when yeah, remember the experiment we did in class. Okay, so when we feel cold, when when heat exits from our body, right? So over here, why do we usually feel cold when his body is already hotter than usual, which is a good condition given to us? So the principle that we want to use, right, is to tell them why we feel cold, right? So why we feel cold. Okay, this is when heat is exiting out from our body. And the second principle that we want to bring in is, why would heat exit from our body, right? Because heat travels from hotter to colder region. Colder region. Okay, and then we can relate to the question. Okay, yeah. Okay, so based on these two principles, right? Okay, because the body temperature increases, heat will exit from the patient. Okay, so when the outcome finally, right, is when body temperature increase, heat exits from the person feels cold. All right, now explain why a jet of steam of 100 gram is more dangerous than 100 gram of boiling water. Now if you were to take a look at the heating curve, now look at this. Boiling water is at a temperature of 100 degrees Celsius. Anything that is after boiling water is the gas, right? And because of that, you know, even if the gas is at 100 degrees Celsius, so let's compare water, let's compare point C, where the substance is maybe fully liquid. Okay, liquid at 100 degrees Celsius. And let's compare point D. Point D is actually a point where you have gas at 100 degrees Celsius. So are they as dangerous, or which is more dangerous than which? Okay, so gas is definitely more dangerous. Why? Now take a look, right? From point C to D, right, there's a lapse of like, I don't know man, like what, about 10 minutes. Like in these 10 minutes, right, it's gaining energy. Okay, so it has 10 minutes worth of energy, more than the liquid at 100 degrees Celsius. Okay, so for boiling water at 100 degrees Celsius and steam at 100 degrees Celsius, please don't write anything yet. Okay, so for boiling water and steam at 100 degrees Celsius each, right, okay, this thing, right, has like 10 minutes. Of course it's not really 10 minutes, right, it varies. Okay, but anyway, let's just put here has 10 minutes more energy. I don't want to add a device. Okay, whatever. So has 10 minutes more energy, right? So you look at this, it has gained energy for 10 more minutes than usual. How do I get rid of this? Wait. Okay, now, so in that 10 minutes, right, it has gained energy. And like when you are going to touch the steam, right, that amount of energy that it has gained is going to be released to you as well. Okay, so because of the amount of energy that's going to be released to you, and the amount of massive energy that's going to be released to you, it's going to be more dangerous. All right, so for boiling water at 100 degrees Celsius and steam at 100 degrees Celsius, steam has more, but the thing is both are at 100 degrees Celsius. So if you talk about kinetic energy, you might be wrong, because the kinetic energy has to do with temperature. Okay, and in this case it seems like their kinetic energy is similar because of their same temperature. So what we're going to talk about here is internal energy. Okay, steam has more internal energy, therefore it is more dangerous, as it may release like more energy to whoever touches it. Okay, as it let's just call it toucher. Okay, you get what I mean now. All right, and yes, we are at the last page now. Factors that affect the rate of evaporation. Okay, if you understand what evaporation is, this is going to be like super easy. Okay, so first thing, temperature. Of course, temperature affects rate of evaporation, because we remember evaporation is when the highest Ke particle actually goes away from the surface, right? So if the temperature increases, okay, naturally your average Ke of particles will increase, and when the average Ke of particles increase, you have more particles that are of higher Ke that will be residing at the surface. Okay, so it'll be like something like this. Maybe it's like 2 particles. So this is at low temperature, versus like at high temperature when you have like much more particles, right, like residing on the surface. Okay, area of exposed surface, also the same thing. Okay, so like imagine you have this, right, and in this area of exposed surface you only have 4 particles, but versus one that has large area surface, exposed surface, sorry, okay, you have like much more probability of like higher particles, particles with higher Ke like residing at the top of the surface. Humidity of surrounding air, we talk about it. Okay, so it is difficult for particles to like go here. Let's say like this humidity is at very high. Okay, what you want to do, right, is that you want to achieve equilibrium. Okay, in terms of pressure. Okay, so like the surrounding air, okay, if like the surrounding air pressure is very low, what will happen is that the water particles from the water will actually compensate for that low pressure by evaporating into that low pressure to make the pressure higher. All right, so what happens when this particle goes here, right, then it will join in the crowd. Okay, and like sooner or later you have like more and more particles joining in the crowd. This humidity will become dense, right, and when it's dense the pressure is higher, less particles will want to like evaporate into this humidity. All right, firstly because they cannot, secondly because like your pressure equilibrium has been reached. Okay, like motion of air. Now if the air is slow versus the air is fast, it makes a difference as well. Okay, I think it's like pretty straightforward. Okay, so like so basically it's like wind. Okay, so like wind causes rate of evaporation to increase, right? The faster the motion of the air, the faster rate of evaporation. Nature of liquid, different liquid evaporates at uh, different rate. Okay, maybe because the energy required by each liquid, right, is different. Okay, the energy required to like increase the distance between particles for say alcohol and say like water is definitely different. That's why like alcohol has a boiling point of I think if I'm not wrong is 78 degrees Celsius. Okay, while the boiling point of like water is like 100 degrees Celsius, right? Okay, and this difference probably come up because of the way they absorb energy and also the way they are structured. Okay, lastly, right, pressure, right, I skip pressure because I think it's the same as point 3. Okay, so that there's no point talking about pressure. Now here are like 5 points, okay, that governs the factors of evaporation. I think it's pretty straightforward, so you don't have to like memorize. Okay, and I think I'll end the video here. Okay, please fill out your notes, and yeah, goodbye.